Last day, we derived the shape for the first law in quantum thermodynamics, where this Q is simply the integral of the trace of the derivative of our state times Hamiltonian, and this W is the definition.
Wait, wasn't it the opposite? Wasn't the work the one with the Hamiltonian and the heat the one with the jumps?
Yeah, I mean.
No, the work is the change of the Hamiltonian and the heat is the one. Yeah. Okay.
1 minute and you're already interrupting me. Exactly. If your state is changing, you have the definition of your hits. Otherwise, if your Hamiltonian is changing, your spectrum, you have heat there, right? That's how we ended the last seminar, and now we are going to move towards the second law. So the second law, as we already know, is related to the entropy production. So we expect that is greater or equal than 0, right? Okay, so we're going to derive this later, but in general, the entropy production in thermodynamics, especially the derivative of the entropy production, is simply the temporal derivative for the entropy of a system plus minus heat, the derivative of your heat term over the temperature, right? In the case that you have a multiple bath scheme, it's simply summing over all of the baths you may have. Okay, and we expect this to be larger than equal than 0. Okay, so let's consider a quantum system interacting with thermal baths, and we are going to compute this. The first term, it's given, as we presented the last day, by the von Neumann equation, entropy, sorry, which is well, in this case we are presenting the derivative of the von Neumann entropy, and we can use here the fact that we have an open quantum system, so this is minus I. You have the Hamiltonian part plus the dissipator part, and you can also use the cyclic property of a trace. So finally you get to an expression like this, basically. It's over R, so yeah, it's over R, which depends on T, Rs. Right? This is what you get in. That is for the first term. And the second one, this shape is kind of complicated, but you can write this down like like this. Where you have the state of your system and the state of the thermal state where the system is, evolving to.
I'm asking, what is theta?
Yeah, theta B is just a thermal state. So you are considering your state in a given state rho s.
But no, but you have theta nu rho s. Is that the same as?
No, this is a D.
This is a D.
This is a D, sorry.
It's a small type of, in the sense that when you wrote the master equation,
Yes.
you wrote only
Yeah.
one dissipator.
Yes, sorry.
And then
Yeah.
in the other case, you expand several.
Yeah.
It's basically for each path you have a different dissipator. So you are evolving your system from a given state, whatever, to a thermal state, right? You have a thermal bath attached to your system, and it's imposing a temperature 1/bit, right? So let me convince you that, let's see, erase this part. Let me convince you that you can write this down as you have dissipator here. The first part remain equal, but the logarithm there will give you to a minus beta h. And you will also have, in case B, a trace of the dissipator part. It's at D rho s t, and the logarithm of the partition function, right? So there's a number, you can take this out, and because of trace preservation arguments, this term is equal to 0, right? You have to preserve the trace of your system. So when you are tracing out this average of the dissipator on your state equals to 0, and you finally get to this thing, which is basically minus k sub b trace of and the Hamiltonian of your system.
So what was the argument for replacing the OST in the logarithm with the thermal state?
Yeah, you basically your system it starts at a given state, wherever, thermal rho s, and since it's attached to a thermal bath, you expect it to evolve to a thermal state of without that temperature.
Okay, but why only the logarithm? Why are you not substituting the thermal state also in rho s of t and
Oh, it's just I just want to take a look. Say minus k sub b beta, and here you have this term. You can recognize it. We saw it last day. This is simply Q, right? Especially Q dot. We saw it last day, and you have 1/bit and the burst temperature here. In the case of B, it's Q/T with a minus. So I'm just trying to convince you that this term can be written like this.
okay, it's a second.
So it's not that it's something. We start from this.
Yeah, just to show that.
Yeah.
So the point is, we are going to use.
I missed the fact that it was a second term. I thought it was continuing from the first.
Okay, I'm going to use simply that expression. The expression can be plugged in here, and then you get to a simplified version of that, which is basically the entropy production over time is equal to minus k sub b, no beta, b, you sum over the number of paths you have in, and then the trace of the dissipator nu over your state, then your state which evolves over time, and you have here the logarithm of the initial state minus the logarithm of the final state, right? It's a pretty nice expression. So what we are seeking is basically some kind of an expression to state this, that entropy production is greater than 0. But in that shape we cannot know. But you can do a trick here, which is basically you can always define, I'm not going to go deeper in this, but you can always define a channel, a CPTP map, like the exponential of the dissipator, which depends on time, since this depends on time, like this, right? For a very small interval, so that when you apply the dissipator over your thermal state, it remains equal. It's basically a fixed point, right?
Okay, let me think about it. The dissipator is the connection of with one bar. Okay.
Yeah, exactly.
Each mu represents one bar.
Yeah, it depends on the. Okay.
Okay.
Right. So you can do some math here, and then finally write down the entropy production as k sub b and the sum, nu in the limit where dt goes to 0 as this relative entropy I'm going to show you right now, minus the relative entropy.
Sorry, Álvaro. Sorry.
Yeah, tell me.
No,
No, I
I
mean,
disagree with what I agreed before, because there you have this tau beta nu, but no, tau beta is defined by beta, because in beta is the temperature.
yeah.
Should this, the other index doesn't mean anything, because for a same temperature you cannot have two thermal states. So beta is the only index you need. So this.
It's redundant, right?
Okay,
You mean?
no, not mu. So now, my question before, so that if epsilon mu is different channels,
Mm-hmm.
how can it be that the thermal state is an eigenstate of different channels at different temperatures? Is it because the differential of theta is very small, or is it for other reasons?
I really don't know.
Okay.
Yeah, this is basically an argument just to state that.
Go on,
Yeah.
maybe we are.
Okay.
Unless this T beta is the
Is the thermal state is the exponential of minus beta h.
yeah.
Yeah, but you have
H
some
is
kind of
the
an.
system, it's not the
Uh,
is the thermal state of the system.
So how can it be?
Okay. So basically, this is used. You can take a look at the derivation of this in the Strasser book, this is by definition larger or equal than 0, right? Because this is the relative entropy of two density matrices, positive, and then also a property of any CPTP map is that if you have this, it will be always larger or equal than this thing. So this is positive, positive, and this will be larger or equal than 0. So finally, you get to the entropy production being larger or equal than 0, which is what we wanted to show, right? And that's for any CPTP map. This from here. If you want to click next to here.
Yeah, but I think it should be. It's important that the
Yeah.
dt goes to 0.
Yeah.
If dt goes to 0, then this is the identity, right? It's not
Yeah, in fact, exactly. If you have this,
I mean, it's not 0, it cannot be 0, it should be very small.
very small, so that you can have this fixed point.
I mean, in general, for small dt, this map you can write as identity plus the dissipator, no? Because
Yeah.
the taper is not indestructible. Now the question is whether or not obviously the thermostat is invariant by the identity. The question is it invariant for all dissipators?
This is my because we have if we had only one bath,
Then it will be
it would be trivial.
Mm-hmm.
But as we have different baths, so this goes back, and now you don't understand when we include the tau beta.
Yeah.
What is the beta?
Are you
Is it-
sure that this is only, he does this assumption for each nu, or that the CPTP map is defined as the exponent of the sum of all the dissipators? Because
No.
then,
It's in Strasbourg, it's defined in this way, like this, right? Because I mean, so this is basically a mathematical trick to show this.
yeah,
Yeah,
I understand this, but the
Well,
question is now the assumption, no? Whether or not
Yeah.
you can have for every nu the same thermal state, no?
And also, this to me is the same as if we go back and back and back and back, we have defined a beta, and we have been working with a beta all the time. You have different baths. What is this beta? Is the because beta is the temperature. You have two baths with two temperatures. This beta is
If you have only one bath, it's clear, right?
clear. Yeah, and if for one bath,
It's
I understand it.
everything.
Then the beta is the beta of the bath. When you go to the CPT map, you define this way, and then it is trivial that this thermal state is eigenvector of the map. And everything is covered. The only thing is, as there are more than one path, I don't know if this beta should be the average temperature or we are assuming that the system goes to a thermal state of a certain temperature that we don't know. This we call beta. This is what.
I think the problem also, I guess the confusion for me also comes with the difference with the two expressions you wrote. The first one, the sigma dot, only has one bath.
Yeah.
And in the second one, you have several baths. But you don't have a Q nu for every bath. It's one Q.
Because I
No, well.
wrote down I instead of mu.
Okay.
Yeah, sorry.
Yeah, it's
so
a-
then
it's a confusion
that
there.
deviation there should have a Q nu as well, no?
Yes, yes,
Every bath has a beta.
yes.
So, okay.
And
Maybe there is some summation somewhere that we don't. Maybe there are.
I'm missing the.
Yes.
Sorry.
So now maybe,
Yeah, this.
so now maybe what does make sense is that indeed this is a thermal state of one beta
Okay,
for each
okay.
nu.
Exactly.
Okay.
So it wasn't lacking the mu.
No, sorry.
No, it's okay, you don't need it. I think
I mean-
just, for each nu you define a
A
beta.
beta
no?
mu. It
The
would
beta
be
nu.
our
Beta
beta
nu.
mu.
Yeah,
Yeah.
No, it makes sense.
So, yeah, it's simple notation. All right. And here you have as well. Okay. So basically, I tried to convince you that the entropy reduction is positive. And yeah, regarding the second law, you can also define several thermodynamic quantities, but they are really not very used in the or at least not commonly used in literature. Like, at least to know, you can define the free energy, right? Like in classical thermodynamics. Yeah, it will basically have two contributions here, simply Hamiltonian. And you will also have the second term related to the entropy. And this depends on T. Right? Which is analogous to the classical case, especially in stochastic thermodynamics, right? You have some kind of sums over x, Ex, and the probabilities, right? And then another term with the heat. Huh? Okay. So if you take that into account, you can write down the entropy reduction simply as some kind of quantity involving the work and this free energy, which is also positive. Right? I'm not going to go deeper in this. If this is equal to 0, you get the maximum extractable work, which is given by the difference of free energy, which is a thing which is well known in classical thermodynamics as well. So, is everything clear more or less? We just simply convinced you that the entropy reduction is positive, or 0 in the case of reversible dynamics. Right? Reversible dynamics.
Must be a trace also in the...
Yes, I forgot. Oh. Yeah. Okay, so let's analyze all these from a different point of view. I will try to connect this thermodynamics with some sort of information theory. I'm not going to go so deep in this. I just want to derive the expression for the entropy reduction. I remember E. In a simple case, it's basically this, right? So we are going to consider simply a system interacting with an environment, and they are somehow interacting, right? And we're going to assume that initially the system and the environment are uncorrelated. So I can separate the states of both subsystems, right? So at a given time t, which I'm going to denote this as rho SE prime, this will be given by some kind of unitary operator, since the evolution of the whole layout I have is unitary. Right? So if we are interested in the state of our system at a given time t, I'm going to call it rho s prime. It's simply, I have the joint state of my system. I'm going to trace out over the environment, right? Discarding all the information of the environment, and what remains is everything which is related to my system. Okay? Simply as it is. Note here that I'm not taking into account any kind of assumption over the path or the environment and the system. I'm just analyzing the whole dynamics given by this, and then I'm interested in the system, so in discarding all these degrees of freedom in this way. This process itself is irreversible. Since I'm tracing out over the environment, right, I have no longer access to that information. That process is irreversible by itself, right? So this can also be done, since Mihalis is very interested in this, by a CPTP map, where this big epsilon is basically a map, right, which does all this. Okay, so in a general point of view, we can quantify this loss, this entropy production, as two terms. One of them is basically related to the amount of shared information between the system and environment, right? And the other one is the relative entropy of the final state of my environment and the initial state of my environment. That is some sort of a distance between these two states. I say some sort of a distance because this doesn't verify the triangular equality, this relative entropy. It is quantifying how much this rho, right, is the mutual shared information between these two subsystems, and this term is how much the final state of my environment is away from the initial state of the environment. Both of these quantities have a very precise mathematical definition. The first one, this mutual information between two subsystems, is simply the relative entropy of rho AB, the joint state, and the state if they were separated in this way, right? And this definition as well is simply the entropy of the first one plus the entropy of the second one minus the entropy of the joint state. When we are saying entropy here, it's the von Neumann entropy, right? That's the first term. I think it's clear in this way. Imagine that they were separable. So if it's separable, this can also be written as a product of this. They are not sharing information, so this will be equal to 0. Okay? And the second one is the relative entropy. Basically, we saw that before, but I'm going to rho and sigma. This defined as the trace of rho log rho minus rho log sigma. Okay, as I said, it's some sort of a distance. And yeah. Okay, this is general. This is what one would expect to have if we are computing this entropy production. This is still not thermodynamics. I'm doing just some, let's say, information theory, but yeah. You can do some calculations here and write down that entropy production simply by using this, replacing this by the von Neumann equation, von Neumann entropy, and computing this with the environment. This can be written simply as the relative entropy of the joint system environment case. Density matrix, sorry, times the final state of your system times final state of your environment. I remember you that this is this happens when you are tracing out the degrees of freedom related to the environment, and with the state of your environment, it's the other way around. Tracing out the degrees of freedom of your system, right? It's very logical. Okay. So this is a generic expression for any kind of environment. But we want to write this down as something in a Clausius way, right? Some kind of term related to the entropy variation of my system, and some kind of entropy flux, right? Something which depends on your system and extra terms. Also in a general way, nothing to do with thermodynamics yet. So let's consider the case we have here. Here, the system and the environment are initially uncorrelated. So you can compute the mutual information in the following way. You will have the entropy of rho s, right, plus the entropy of the state of your environment minus the entropy of your unit state.
These are primed, no? Because you take the expectation of prime.
Sorry, I'm going to compute it for the initial state. Why I'm going to do this? Because I know they are separable. So this will be equal to 0. Since the initial state is a separable state. There is no mutual information, right? From here, get that the entropy of the joint state is simply the entropy of the state of the system plus the entropy of the state of your environment, right? But we are having a unitary evolution, and the von Neumann entropy is invariant under these kind of evolutions. So this will be equal to the entropy of the unit state at the final time, right? Okay. With this, let's compute now the mutual information shared for our final state. For the same argument, this will be simply equal to the change of entropy in each of the subsystems, right? Because the expression will be similar to this one. This term will be equal to this term, and well, this will be like the variation of mutual information is given by the difference. This is 0, so one would get this term here. Is it clear? Simply, we consider that the evolution is unitary and the system of the bath and environment are initially uncorrelated, given by this expression. Okay? So, once we have the expression for the mutual information shared, we can substitute this and compute the entropy production. We'll have that this first term, so this will be equal to these two sums plus the relative entropy of the initial state of your bath and the final state of your bath. You can, I'm going to move them. You can extend the second sum you will get the change of entropy in your system. It doesn't, I'm going to leave it the same way, plus the entropy of the final state of your environment minus the entropy of the initial state of your environment. This is simply the variation of entropy. And then the second term is the trace of rho e log rho e, both with prime, minus the trace of rho e prime log rho e. This is simply minus the entropy of the final state of your bath, which cancel out with this one. And then you will get the variation of the entropy of your system plus the trace of rho e minus rho e prime times the logarithm of rho e, which is in the shape we are looking for. Some kind of term which depends on our system and some kind of entropic flux. Okay, as I stated before, this is a general expression for the entropy production. It doesn't depend on the state of the shape of your system, nor the state of your environment. It's general, completely general. But now we're interested in thermodynamics, so let's make the following assumption. Imagine that in the case we presented at the beginning of the derivation, instead of having some system interacting with a general environment, we're going to make it interact, as usual, with a thermal bath, right? So let's compute the entropy production. We have this term, which only depends on the system, plus the entropy flux, which only depends on the state of your bath. The bath, if it's thermal, which is what we are assuming, is given by a given state. So, from here we can compute the second term. Rho s plus the trace of the initial state of your bath and the final state of your bath, and the logarithm of rho e. So here you will have the initial state of the bath, it's a thermal state, minus you. We're not going to make any assumptions on the final state of the bath, and then the logarithm is minus beta h. There is an extra term, but yeah. It's simply a constant. I'm going to take out this beta here and change the sign of this, and you simply have you get to the trace of the Hamiltonian of your bath, and the change of the state of your bath. This is the final state it's going to, and this is the initial state. So this change in the state of your bath and this trace concretely can be identified as the heat which your bath is, pulling to your system, right? Yes.
Yeah.
You get to the second law of thermodynamics, and we obtained it only by discarding the degrees of freedom of your bath, tracing out the state, and also only assuming that initially your bath is in a thermal state, and you get to this.
And that they are uncorrelated.
And they are correlated, exactly, at the beginning.
So can I ask? Okay, so it's three assumptions, right?
Yeah. Initially uncorrelated.
Uncorrelated, thermal state for the bath, and what was the third one?
No, only
Just
two.
these two,
Yeah.
right? Okay. Is there does anyone know how to rederive this kind of a similar concept if either one or both of those assumptions don't hold?
I really don't know what to say. I do have to say that.
In particular, okay, let's do one. How crucial is it to assume that the bath is in a thermal state, for example, in all this derivation?
It's just the final step of the derivation, right?
No, but how crucial is it?
Well, when does it play a role?
Yeah. It's just that, I guess it's just at the end, no?
Yeah, exactly. Yeah. From here.
Yes, that's the step is to essentially change the relative entropy in this expression here, no?
Mm-hmm.
Otherwise, you would have to calculate the relative.
Exactly. The one thing I should point out, one thing is the fact that, this QE is the energy difference in your bath, right? In this case, we have it's equal to the energy difference in your system, right? But in general, you wouldn't have this equality. So what is left in this balance is basically work, quantified as work, right? A more profound discussion on this can be, well, everything is taken from the review by Gabriele Landi and Paternostro. You can, the reference is basically right. It was published in Review of Modern Physics in 2021. Yeah, all this is explained there. And they also tell us that there might be some work involved, especially in the unitary evolution of the joint system plus Buffet system. Yeah. Okay. Do you have any doubt about this? But what we have assumed here is without any kind of lack of generality, right? Simply, this can happen encoded in U in the unitary process, but it might not affect to the final result.
So in principle, you want the entropy production to be minimal, right?
Why?
Well, you want your system, you want all the changes to happen to your system. I should say this. You want the entropy production ideally to be just a change in the entropy of your system, no? Because then you would only do work.
Yeah.
Right? Okay. So I don't think they're looking at it the right way.
Why?
Because I can, so if I take this picture, closed system and the system inside, in information theory there's another concept that people use, which has to do with how information, so your system is subject to a channel, which is what you do when you trace out, and then you can ask, okay, in what state can I prepare my system? Quantum information that leaks into the environment is as little as possible. And in this picture, that would correspond to essentially minimizing the heat that comes out. Okay?
Yep.
If you translate this picture into information theory, essentially what people are saying is, okay, can I construct an error correcting code, put my system, such that it doesn't, the environment doesn't affect all the changes happen unitarily inside this system. Okay? And then there are tools for this to quantify these kind of things to assess exactly how information leaks. People use this concept called the coherent information, which is very much related to this concept of flux. Because this coherent information, essentially what it does is it tells you, it quantifies how much information travels from the system to the environment.
Yeah, I think it's in a thermodynamic context, it's clear why this is a flux, right?
Yeah.
In that context, I mean, it's also clear in terms of information,
I know,
right?
but you have the additional
That's
thing in this coherent information where you get to this flux because it depends on the state of the system, okay, and on the interaction. And you, in principle, what you are attempting to do is, okay, you say the interaction is fixed, I cannot change it, but I can change the state of the system. So I can ask, what is the best state to prepare my system so that this flux is minimal?
Yeah, I guess you can play with these two quantities, right, to get the minimum. Yeah. Another thing I like to point out is the fact that we have named the change in your bath as heat, the energetic change in your bath. Okay, that's a matter of notation. If you have this unitary process, there might be some kind of encoded work you're not considering, but we haven't used that for the derivation. It's just, okay, if there is no work involved in the unitary evolution, this will be that way, but in general, it doesn't have to. So one would get also some shape of for the first law. But in this case, you are defining work. I mean, you define this as what remains from this balance, which it's not of your interest in this derivation, but it's there, right? So with this, we conclude the seminar. Simply one thing. Obviously, if you have a multiple path scheme, you just have to sum, right? Which is an obvious thing. So the next week we will conclude the seminars with the applications, basically to batteries and engines. I think it's a very nice point to reach once we have taken a look at all of this. So thank you for coming and see you next week. Yeah.